What specific problem does the TINA method aim to address in the context of language models and reasoning tasks?
The TINA method aims to address the challenge of enhancing reasoning capabilities in language models, LMs, while minimizing computational and financial costs. Specifically, it seeks to improve multi-step reasoning abilities, which are crucial for complex problem-solving tasks, by utilizing a compact 1.5B parameter model and employing low-rank adaptation, LoRA, during reinforcement learning, RL. This approach allows for efficient parameter updates, enabling the model to learn effective reasoning strategies without the extensive resource demands typically associated with full parameter training. By focusing on a tiny model architecture and a cost-effective training pipeline, the TINA method democratizes access to advanced reasoning techniques, making it feasible for broader research participation. Ultimately, it aims to cultivate robust reasoning capabilities in small language models through economical means, thereby addressing the limitations of traditional, resource-intensive RL methods.
How does the proposed method TINA work? Illustrate it step by step, including details on the architecture and the training process involving LoRA and RL.
The proposed method TINA operates by utilizing a compact 1.5B parameter model, DeepSeek R1 Distill Quen 1.5B, as its base architecture, which is selected for its initial reasoning aptitude due to its specific lineage and distillation process. The training process involves two key components: low-rank adaptation, LoRA, and reinforcement learning, RL. First, during the RL phase, TINA employs a GRPO-style algorithm to facilitate efficient learning from verifiable reward signals, allowing the model to explore various reasoning paths and adapt its output format without extensive computational resources. LoRA enables the model to modify its behavior by training only a small number of new parameters, which preserves the base model's pre-trained knowledge while focusing on structural adaptation for effective reasoning. This combination results in a cost-effective training pipeline, where TINA models achieve competitive reasoning performance with significantly lower computational costs compared to full parameter training, demonstrating the effectiveness of the LoRA-based RL approach.
Can you provide a specific example to demonstrate how the TINA model processes a reasoning task, walk through the main steps, and explain the output generation?
The TINA model processes a reasoning task by utilizing a structured approach that leverages its low-rank adaptation, LoRA, during reinforcement learning, RL. For instance, when tackling a problem from the AMY24 dataset, the model first receives a multi-step math problem that requires logical deductions. It then generates a reasoning trace by breaking down the problem into smaller, manageable steps, effectively mimicking the step-by-step reasoning format that is rewarded during training. The model's output is guided by verifiable reward signals, which assess the correctness of each logical deduction made throughout the reasoning process. As the model iterates through potential solutions, it refines its output based on feedback from these rewards, ultimately producing a coherent answer that reflects both the initial problem and the reasoning steps taken to arrive at that conclusion. This structured output generation is crucial for achieving high accuracy, as evidenced by the TINA model's competitive performance on reasoning benchmarks.
What are the theoretical or practical advantages of using the TINA method over traditional full-parameter training methods for language models?
The TINA method offers several theoretical and practical advantages over traditional full-parameter training methods for language models. Firstly, it utilizes a compact 1.5B parameter model, which significantly reduces computational and financial costs, allowing for a more accessible experimentation process. Reproducing the best TINA checkpoint costs only 9. Secondly, by employing low-rank adaptation, LoRA, during reinforcement learning, RL, TINA achieves substantial reasoning performance with minimal parameter updates, demonstrating that effective reasoning can be cultivated without extensive retraining of the entire model. This approach not only preserves the base model's pre-trained knowledge, but also allows for rapid adaptation to specific reasoning formats, enhancing efficiency. Additionally, the TINA models have shown competitive or superior performance compared to state-of-the-art baselines, achieving over a 20% performance increase on certain benchmarks, which underscores the effectiveness of this economical strategy. Overall, the TINA method exemplifies a paradigm shift towards minimalism in model training, achieving robust reasoning capabilities with significantly lower resource requirements.
How did the authors validate the performance of the TINA models? What datasets, metrics, and experimental designs were employed during the evaluation process?
The authors validated the performance of the TINA models by conducting evaluations across a suite of 6 reasoning benchmarks: AMY 24/25, AMC 23, Math 500, GPQA, and Minerva, which encompass a range of mathematical and scientific reasoning tasks. They employed a consistent methodology for all baseline evaluations, utilizing the VLLM inference engine and maintaining a fixed hardware configuration of 2 L40S GPUs to ensure comparability. The primary metric used for evaluation was the Pass-at-1 performance score, which reflects the model's ability to correctly solve problems on the first attempt. Additionally, the authors performed a comprehensive re-evaluation of key baseline models to establish reliable comparisons, ensuring that all scores were derived from a standardized set of inference parameters. The results indicated that the TINA models achieved average scores ranging from 48.16% to 50.60%, demonstrating significant improvements over baseline models, despite the resource constraints of using parameter-efficient tuning.
What are some limitations or potential drawbacks of the TINA approach, particularly concerning its architecture and method of training?
The TINA approach, while effective in enhancing reasoning capabilities through a minimalistic architecture and LoRA-based reinforcement learning, does have some limitations. Firstly, the reliance on a smaller 1.5B parameter model may restrict the breadth of knowledge and complexity of reasoning compared to larger models, potentially limiting its applicability in more intricate problem-solving scenarios. Additionally, while LoRA allows for efficient parameter updates, it may not fully leverage the extensive knowledge embedded in larger models, which could lead to a trade-off between reasoning depth and the model's overall performance. Furthermore, the focus on rapid format adaptation might result in a lack of comprehensive understanding, as the model could prioritize structural output over deeper conceptual learning. Lastly, the cost-effectiveness of the TINA approach, while advantageous, may also imply that the model's performance is inherently constrained by the limited computational resources and training data utilized, potentially affecting its robustness in diverse reasoning tasks.